Okay, welcome to this last lecture in this semester for machine learning. So last time we looked at kernels. We started to look at convolutional neural networks, and here was one example kernel, and you see how by sliding such an example kernel systematically over the input. So here you have the input. You take the kernel and lay it over this input and produce an output value. And you do this by placing it in this position, in the next position, and then you continue sliding until you get to the last position. And so as an output, every position leads to one value. And with this example kernel, you would produce this kind of output, which is just one pixel smaller to the left, to the right, to above, and to below than the original input. And initially people developed such kernels manually, but then there was the idea, why don't we learn them? I mean, these are parameters, so we can just learn these parameters, right? Now, especially when we consider how does this work relatively to parameter sharing? So let's say this is our input, and this is the next level. We are used that we have complete connections, right? So every input unit is connected to all the units on the next layer. This is no longer true when you look at such a kernel. What happens really here is that when you have input units, now let me just look at input units that reflect, for example, this first line. Then in this one-dimensional picture, this input unit would be connected to only three next hidden units. And this input unit would be connected also to, well, actually, let me see. This one would be connected to this. This is even wrong. At the borderline, it would be less. The next one would be connected to these, and this one would be connected to these. So most of them will be connected for this kind of kernel, just considering this one line, to only three next hidden units. Of course, this is what I now do is, with this picture here, I simplify, because, for example, this input unit here would not only be connected, let's look at this. This unit here, this would participate in this movement, but also in a downward movement. So it's a little bit more complicated than in this one-dimensional case that I sketch here. But the point is, we don't really have this picture, every input connected with every hidden unit. But we have a much sparser connection from the input layer to the next layer. And furthermore, how do we compute the values? The computation of the values are defined by the kernel. And the kernel are nothing else than parameters. So these parameters here, whether we put them here or here or here, they are the same parameters. So the parameters that I use in this upper left part are the same as the parameters that I use in this lower right part. So, well, when I arrange this further, I have parameter sharing, how these hidden units are informed from these previous ones with how these hidden units are informed by these previous ones. And I get the same kind of parameters. And so when I now adapt the weight here, this means that I do the same adaptation here. So that means, of course, compared to this fully connected network, I have a much smaller number of weights that I have to learn when I just learn this kernel here. Okay? And that, of course, means that this possibility to extract, for example, here vertical structures, is a capability that I learn by such a kernel. Now, of course, the kernel that I learn will not be exactly this one, will be a different one, maybe some small values different from 0, so it will be a more complicated kernel that I learn. But the kernel that I learn will apply to this upper left part as well as to this lower right part. And this is something I want, because in the end I want to recognize a cat no matter whether it's in the upper left part or in the lower right part, right? I want to apply the same kind of recognition algorithm no matter where in the picture my cat is. And of course we have a very high dimensional input. You see, this is a very high dimensional input because every pixel is an input. So even if this is just 100 by 100 pixels, we have 10,000 inputs. So obviously, having such a connection would be horrendous. If you have 10,000 pixels here and 10,000 hidden units here, that would give you, of course, already 100 million parameters. A huge space. Very hard to learn. If you do this parameter sharing, on the other hand, what you learn maybe such a kind of a matrix, which is just here 5 by 5, 25 parameters. And what we will do is we will not only learn just one such kind of a kernel, but we want to learn several kernels because we want to recognize vertical structures, horizontal structures, diagonal structures. And these structures that we learn are just the first very primitive structures that we can recognize. And once we have recognized these in the layer following after that, we will learn more complicated structures up to the point that at some point we can understand, is this a cat or is this a dog? Okay, so this is the to do here, learning these kernels, always the same ones, and always apply the filter with the same weights uniformly over the whole input so that you have a parameter sharing when you think in terms of a fully connected network. But you don't actually, of course, implement it like this. You don't implement it such that you have the same weights over and over again. But conceptually, you can think like this. Okay. Now then, of course, what we still have this very large picture, let's say 10,000 inputs. And now we need to condense it to fewer pixels because we want to abstract. In the end, we may just want to decide between cat and dog, right? So it doesn't really make sense to have such a very high dimensional representation. And we want to extract the essence. So one thing that is done is the dimensionality reduction. And the very simple thing is max pooling. Yeah, you look at such a region. And in this region, you just determine the maximum number and you transfer them here. This is the 8. Now, if you look at this region, the maximum number is 6, so you transfer them here. So it's a stupidly simple way of doing this, but it works. Of course, there are other mechanisms. You can do average pooling, etc. So there are different ways of reducing the dimensionality. Instead of the 16 inputs here, you only have 4 inputs as an output. And again, you slide this over your input to do this dimensionality reduction. So how does a simple end-to-end convolutional network look then? You have your input image, rather high dimensional. Then you apply these kernels. And as I said already, you do not just use one kernel, but you have a whole set of kernels. And typically what you also do is, since this is applying the kernel is a linear operation, which you saw already last time when we computed this. This is just a weighted input, right? So this is a linear operation of your input, yeah? There are different strategies how to do this. So this is one possibility, but I cannot guarantee you that some papers didn't do it differently. I mean, you want to certainly cover all the input space, but whether you have a stride, I mean, that's mentioned later. Typically what is also done, and well, it also appears on some later slide, is here it appears that we always move by a stride of one, just move one position. That's also typically not done. Typically, you move a little bit more to save computation. But you can also do it like this. What is exactly better in terms of quality, I cannot predict. It depends really on details, right? This is typically stride, and here we have a stride of 1, and for the max pooling example, we have a stride here in this example of 2. So you move this kernel, this max pooling kernel, it's not really a kernel, it's the wrong word, but you move this overlay here by a stride of 2 to the right. But this is not, wouldn't claim that this is the only possible solution. Okay, so input, then you have your linear operation, and on top of that linear operation, you apply something simple like ReLU to include a nonlinear operation. And now what have you done here? You take this image, you run, let's say here, 5 different kernels over it. 5 is not enough typically, but let's say for this example 5. Then you have multiplied the input space. Of course, you save like 1 pixel here at the boundary, but aside from this minimal saving, you have multiplied the input space by 5. And to then do a dimensionality reduction, you apply for each of the 5 outputs the max pooling. So with the max pooling, then you reduce it again. So you see, you expand and reduce. And then you repeat the same procedure. You have then the next convolutions with different convolution matrices, and you learn these ones here. Well, here you don't have to learn anything because we just take the maximum. And then you learn these convolution matrices, and you do this for several steps. And then hopefully you have for each of your different inputs a semantically meaningful feature representation. So you have learned what are the features that are in your set of pictures, and you have a fully connected layer here that leads to an output on which you typically have a softmax operation to classify into cat or dog. And this is the architecture that started the deep learning hype. Oh, cool. You apply it for one entry. So you have here, for example, we would be here. You would have one output, and you apply ReLU to this output. Well, and you do this for all the outputs. Yeah? How do I choose what? Sorry, I just couldn't understand. Sorry, you have to really shout such that I could hear you. I'm not sure what you mean with which order. You just learn these matrices here. Is different than this one. Yes, these are different convolution matrices. The dimensionality of how large they are, that's a hyperparameter. I don't understand what you mean with putting things first. I mean, these are parameters, matrices of parameters. And these are just like weights that you learn. That's it. So there's not that you say, here I have a matrix and now I put this first or second. No, no, no. I mean, these are parameters, your betas or W's, however you call them. And you have your whole, you have from your input to the end, which is the classification label that you have on your images. And you run the whole thing. You do your forward propagation. And you compute your softmax. And the softmax gives you something like, this is most likely a dog. Then you compute your loss. And you do all the back propagation to reduce the loss. And so everything is as you learn for the fully connected layers, only of course when you do this parameter sharing in this way, you have a little bit of different computation because of the parameter sharing. Okay? So, I mean, this is really always the power of these mechanisms, that you have an end-to-end machine learning process. And that's what you should typically work for. Because when you do like sequences, the problem is that the errors, let's say an old pipeline was exactly that you in a pipeline optimize individual parts. But what happens when you do this? So let's say this is your input. And then you have one black box mechanism. And then you have another black box mechanism. And you somehow write this down or you learn it. And independently from this one, you write this down and learn this. And in between here, you just forward information forward. The problem always is that here you do some mistakes. So here you have one kind of mistake, for example, some accuracy reduction, accuracy loss. And then with already a wrong output, you go into the next module, and then the accuracy losses, they pile up as you go forward. The advantage of such an end-to-end infrastructure is whatever mistake you do here, you fully backpropagate through all the different layers in order to minimize the loss. And this is really the one core message that people learned over the years in machine learning, that you really try to reduce this mistake that you do here and improve all the parameters in all the different modules that are somehow involved. So that's something you should always strive to do. And yeah, so that's the whole pipeline. And so this is then the realistic architecture, not the most modern one, but the one, as I said here, that started this whole hype, because there was a jump of being able to classify pictures, cat stocks, or something like that, by this architecture. And so what do we have here? Just to give you an idea of the dimensions. So you had an image 224 by 224, right? So that's already about 40K pixels. You have 3 channels. The 3 channels for RGB, red, green, and blue. So this already means that you have an input in this order of 120K values that you hand over. Then what you do is you have convolutions of size 11 by 11. So these convolution matrices, 11 by 11. What is not fully clear here is this specific paper implemented this on two compute nodes. So they could do computations in parallel. And so the 2 pipelines are identical. There is one up here and the other one identical down here. And there are only a few places where they exchange information. Like here is some communication between the 2 compute nodes and here. And of course, what is also great about these convolutions is that these are local computations. Yeah, you can locally forward the values because you only look in your neighborhood. You don't need to send messages over to the other compute node that often. Yeah, some communication is needed, but not that much. Okay, so you have then here the 3 channels. You have your convolutions. The convolutions, of course, can also, this I don't remember now, whether these convolutions was an 11 times 11 times 3 convolution. I would have to look this up, I have to say. But it's easy to imagine. You don't have to limit your convolution to the 2-dimensional. You can have your convolution also as a kind of 3-dimensional matrix with 11 times 11 times 3. And now this is then results in a depth of 48. So obviously you take enough different kernels. So you produce here a depth of 48, and you still have the same kind of 224 by 224, or maybe this is a little bit reduced to 220 or something like that. So that's, you still have a much larger value space. And what you see here is that it says here 55, not sure what the 55 stand for here. And what you do here, the next step is a max pooling. And with a max pooling, you have 5 by 5 by the whole depth. Max pooling operators that condense reduce the dimensionality. And after that, you have the next input, which is only 128 by 128. And you have again convolutions and max pooling. And so this is, you see, instead of having many inputs in few channels, you have increasing number of channels, 48, 128, 192, where each channel then stands for a different combination of, where each channel stands for one kernel, but the combination of kernels stands for a more complex feature. Yeah, you can imagine that a nose, for example, would of course lead to a certain arrangement of kernel of values resulting from the kernels, but they are put for this position then put behind each other, so to say. And and in the end, you have here a representation of 2,000 hidden units here and another 2,048 hidden units here, so 4,000 values. And these are now abstract representations of features that help you to classify the objects. We don't know what these features really are. Yeah, I mean, of course, you can explore this. You can try to find what happens when I switch, when I backpropagate and I switch such features on or off. Many of these features are about textures. What we would expect, since these networks are so good, is that they will be very good at recognizing shapes. They aren't. They're very poor at recognizing shapes, actually. But they're very good at dealing with textures and very good at dealing with local features of the image and then combining local features of images. Yeah, and in the end you have 1,000. This is the last layer. And there you do a softmax over the 1,000 categories that they used, that they had labeled. So they learn the softmax over these 1,000 categories. So here you can just go through that. Yeah, the stride is the information how much you move a kernel. And if the stride is less than the kernel size, the kernel applications overlap. Yeah, that's what I showed you with this toy example, when we had a stride of 1, and then they would overlap maximally. And typically that's not what is done here. Here it is mentioned there's a stride of 4. So if you have this 11 by 11 matrix and you have a stride of 4, so they would overlap with regard to 7 of the values. Here the strides are not mentioned, so one would have probably even to look into some of the code. When I read the paper, I could not read all the details from the paper. One would have to look into the code too in order to find all the details. How do they do regularization? One thing was by data augmentation. I showed you already last time that you would shift the pictures. Yeah. This place it was 4. Yeah. Yeah. So this should be smaller. That's true. Maybe this was. Oh yeah. I was mistaken when this must have been 55, well, which is about right. It's 55 times 4 would be 220, and then at the boundary you lose a few things. And yeah, so I said this wrongly. Thanks for the correction. So you have this small, I mean, it looks here geometrically like it would be the same size as here, but it's wrong. It's like 55 by 55. Yeah. Okay. Yeah, regularization by data augmentation, producing more pictures with the same label, and by dropout. Yeah, and with dropout really sort of like silencing some of the units with certain probability or the connections. This was from 2012, and the most recent ImageNet competitions, here are the competitions, they are better than human performance. But of course, the human performance is done on a somewhat unnatural task. Here is an image, label that. And then the humans are not that great. I mean, still, when you ask a human who's driving a car to recognize the problematic obstacles on the way, the human is still much better than the automatic mechanism. But if you give them sometimes a somewhat artificial task, which is also tiresome, and you check for how good are the humans at labeling this, the machine is actually better doing this with this predefined vocabulary. And the unexpected errors that that the machine does, they are very different. So the human and machine errors are different errors. Okay, so this is already one important class, CNNs. Now another very important class are RNNs. So what we seen so far, we have seen some input being processed by some multiple layers, and we have an output for that. However, what we could also have is one input and then a whole sequence of operations, all leading to outputs. So for example, when we give as input an image, we may want to tell the system, give me a caption for this image. So output should be Taj Mahal at daylight, or a cat playing with this and that. So then of course you have one input. I mean, what you don't see here with this block architecture, you don't see that the image may of course be 40K pixels, and maybe the output here would be just 3 words or 10 words. So this is not so clear here. So you don't have to understand this as being proportional to some value size. That's not necessarily the case. Okay, so anyway, you provide one input, and then some sequence is processed, and you get a caption. Would be one example. You could also have many to one. For example, you give a text as an input, so you have different words that are represented. For example, each word is represented as a one-hot encoding, and in the end, you want to classify, is the word positive word, like good or great, or a negative word like bad or violent. So this would be a classification coming from a sequence. You may have sequences to sequences. For example, machine translation is of that nature, that you provide a sequence of words and you want to have a sequence of words out. And of course, what you need to do is, this is not a one-to-one translation. Yeah? If this word is translated here, it is not necessarily the case that this word is translated here, because the translation depends on the context. So when I give you some German words, the context may influence how I should do the translation. Yeah, I mean, you all will have experienced this, no matter what your mother tongue is. When you translate to English, you may have to choose appropriately. And the last one would, for example, be a video classification. Many to many without, I mean, here you may have some delay. Maybe even for the first word, you want to understand the context before you translate it. And here, so this is a different many to many where you classify videos just on the frame level, but it may be very difficult to understand the scene. I mean, typical example is when you have a shot of a plane, it's very hard to say whether the plane is departing or landing. But when you have a sequence of frames and you see how the plane approaches the ground, then it's, you know, okay, it's landing, or the other way around, it's departing. Okay, so what many models do in order to deal with these sequences is to have a neural network where you have a time-indexed hidden layer or several time-indexed hidden layers. And the idea is that your function has weights, like we always had, and you have some input vector at some time step. So a time step would be here. This is the first time step, second time step, third time step. So whether it's time or position of a word, just reflected here as a time step. Or a video, the video of the first frame, second frame, third frame, this would be the temporal evolution over time. So we have some input at some time t, and the output depends, of course, on our weights, but also on the old state. And the old state is something that is handed over from the processing to the next step. So if this is x and x consists of x1, x2, x3, let's say we give x1 here, the RNN looks at x1, it also looks at the previous h0. Well, h0 needs to be initialized somehow. That's actually not a trivial choice how to do this. Let's assume it's just randomly initialized, but that's often not very good. Anyway, so let's assume it's randomly. So it looks at the h0 and it looks at x1 and then produces an output. But it also produces the h1, and the h1 is forwarded recursively. So if x2 comes here, the network looks at x2 as well as h1 and produces the next output. So here you see this new state h2 depends on h1 and x2. And so this is the principle of common to all recurrent neural networks. We don't go into that many details here because LSTMs have more features. They do not only have this remembering unit, they also have a forgetting unit. So where the idea is, what should you delete? And the nice thing is that you are not really limited immediately in looking back. Well, it's not fully true. The trivial RNN tends to forget rather quickly because everything that is to be remembered must be communicated via this time-stamped hidden vector. You really have to shout, sorry. So the RNNs that we look at here are also deep neural networks. I mean, anyway, this notion of deep neural networks is a little bit an advertising notion, right? So there, it has some historic meaning in the sense that in the past, let's say in the 80s or 90s, people looked at networks of depth 2 or 3 or 4. And later on in the zeros, people had GPUs and understood how to work with GPUs and had much more computational power in order to deal with deeper networks. But in the end, a deep neural network is just a neural network. And there is no definition that it's deep as of 3 hidden layers or 4 or 5 or 10. Yeah, there's no clear boundary. And in the same sense, a recursive neural network is just a neural network. It can have many layers, and this is not really pre-up defined. Yeah? Of course, when you look then at papers, you will have different amount of layers. The CNNs, by the way, this is still rather smallish, because here we have 1, 2, 3, 4, 5, 6, 7, 8 layers, but now you may have like double, 3 times as many layers in the larger models, and even more so in the large language models. But I mean, there is no golden answer to how many layers you should have, because it gets more challenging. You need more data to learn well, and we also work on how to reduce the number of layers by other mechanisms. But it's an ongoing development of how have sufficiently many but not too many layers. This is not a very satisfying answer, I fear, but it's just the way it is. Okay, so yeah, the recurrent neural network, some output from time step t is input to the next time step t+1 for processing. We, for example, use RNNs, rather LSTMs, that also have this forgetting function, for multi-step prediction of vehicle motion. Yeah, so you learn, for example, for a ship or for a drone, how will the ship or the drone move given certain kind of control input. And you do not only learn this for one time step, so like for the next second, but you try to learn this to predict it for the next minute or next 10 minutes. Because, for example, in the case of a ship, you want to plan the route such that you use as little Schiffsdiesel, not sure, some gas, as little gas as possible, yeah. And of course, you want to keep it under control and lead it to the target. So you want to do multi-step predictions. And the language models, there was a new technology that I don't have in the slides here that we handle in the foundation lecture class in fall. These transformer architectures where you do not have this infinite possibility and you rather just model a certain length and you look at how for a length of input, like typical would be like 500, maybe a bit less. You look at how the different inputs interact with each other. But now there is a development, research ongoing, that some of the more recent architectures, they do not use these transformer architectures, but they use again RNNs. For example, Sepp Hochreiter, who invented LSTM together with Schmidhuber in the 90s, I think, they now have a new model they call XLSTM. Well, they compete against the likes of ChatGPT, but with less money, but still, impressive amount of money, but not in the billions, but only in the 100 millions. Yeah? And so now the paper is even out. When Sepp visited us, like, when was that? Early spring, then the paper was not out yet. Or Mamba is a state space model, also a bit like the RNN. So these are competitors to the current transformer models that underlie most of the recent language models. So when to use deep neural networks? This is also some general consideration. And the when, of course, also implies that you should not always use a deep neural network or a neural network. I mean, if you have a simple task, you may be better off with logistic regression or support vector machines or whatever, yeah? And you should always start, I think, or not always is too much of a word, but usually start with a simple model. Clearly, when you have complicated input like images, text, etc., there is basically no way around using some deep neural network. But when you have database tables, you probably want to not to start with deep neural networks. So, what is the general problem? A general problem in machine learning is the curse of dimensionality. And when you are in a small dimension, for example, when you have records about, let's say you have a database table about people, what is their income, how many children do they have, and another attributes, and you predict whether they are happy. This is a low-dimensional problem because you basically have 10 attributes and you try to predict the target attribute. When you have images, like the ones I showed you, you have this 40K pixel values. So this is a high-dimensional problem. Of course, high dimensionality doesn't start with 40K. You also already have the problem when you have very large information systems and you may have thousands of columns. For example, when you have a medical patient, I remember when we collaborated with some company who dealt with transplantation patients, and they had a taxonomy of attributes that covered 10,000 different attributes. Because the problem with transplantation patient is that they have a very long medical record, because if you get a new kidney or so, for the rest of your life, you are a transplantation patient. And over the time, many problems may arise and interact also with just the normal problems that every person has as he or she gets older. And so they have really this huge taxonomy of attributes that they consider in order to allow effective retrieval. And so already then, you don't have like 10 attributes, you have 10,000 attributes, and they are all meaningful, describing some medical state. You have a problem, because the problem always is, in a way, that your input X is classified or some value is predicted based on how close you are to other neighbors. Yeah? I mean, all the different mechanisms you have seen now in the course, they are always related to proximity in some space. The way how this space is partitioned, that varies. Yeah, so support vector machines do a different partitioning than neural networks, different than logistic regression, different than decision trees, different than backing boosting, etc. But they all do somehow, when you think of classification, a partitioning of the space. And so the principle always is that instances that are close to each other are more likely to end up in the same category. And you try to optimize the partitioning such that this happens. And then the question is, who are your neighbors that you are similar to? Now, if you have just one dimension or 10, finding these similar neighbors is easy. But what if you have 10,000 or 40,000 dimensions? there is a mathematical problem that's then associated. And the problem is that an object in high dimensionality has many neighbors in roughly the same distance. Maybe let me rather plot this. No, I wanted to. No. Let me draw this in the extreme. So let's assume we have one dimension. And you have data here. And now you have a new piece of data. It's very easy to say in one dimension which data items are close to this new object. Like this one and this one, they are the closest. Very, very trivial. And this distance to the closest is very different than the distance to this one here. Yeah, because this is like 3 times the distance. Very easy. Now, what happens? What happens? What happens when you are in many dimensions? So these are all, and by the way, when you look at this problem, what you do is you assume that you have, for example, a normal distribution here and a normal here, and you try to determine to which normal distribution you are the closest. What happens now if you have many dimensions, and in all these many dimensions you have normal distributions? Yeah? Then as you increase the number of dimensions, the expected distance for random samples becomes more and more and more similar. And this is expressed in this diagram up here, that you look at don't want this anymore. You look here at the certain distances, and you ask for how much volume is in this distance. So you basically look for what percentage of objects do I find at this distance, and this in a cumulative manner. And for one dimension, as you change the distance and as you have here some normal underlying distributions, you have pretty much like a linear growth of volume at a certain distance. But as you increase the dimensionality, more and more and more of this volume happens at about the same distance of closer to 0. Which means that all of the instances, all of the existing objects are in about, or more of them, are at about the same small distance to you. Sorry, not small here. This is just the distance around this radius of 1. So every distance-based algorithm, in the end, all the algorithms are distance-based. They have more and more problem to decide which are your closest neighbors. Okay, so this is the problem of dimensionality. We also have this for deep neural networks. The one advantage that we have for deep neural networks is that they can warp the space. So basically you can imagine this like a rubber sheet. Yeah? You can warp the rubber sheet, you can pull it apart, and especially for such a neural network, you can warp it in places where you need to put more attention. So you only partially warp it in order to be able to better delineate examples in such a region. The second reason why you might use deep neural networks is local constancy. The KNN, SVM, so they all have the local constancy, which is basically f of x is approximately the same as f of x plus epsilon. And what you want, of course, what we desire actually is that you learn the blue curve and not a polynomial which oscillates. Well, you have here this partitioning of the space that I told you about. But what you also then have, when this is your training data, so you would have example objects here that are black, example objects here that are white, etc., etc. So how would you expect should the surrounding area look like? What would you expect? Yeah, you only have data in this region. What would you expect is in the region around? If there's no data from that yet, maybe I should have made it gray. Yeah? I'm not sure I understood this. So my argument would be, when this is your training data, all the training data is here, you don't have data about this region or that region or that region or that region. I would expect that the checker-like pattern just continues. What do the partitioning algorithms learn? They learn this. Because you have basically learned, okay, here is, for example, white. So everything which is closest to the known white also becomes white. Here is black. So everything which is closest to this black is also black. And it doesn't really matter whether you have KNNs or decision trees. I mean, yeah, the exact shape of the boundaries will be different. But the basic principle that you take the nearest neighbors, more or less, makes all of this region black. What you don't have is recognizing of this pattern. With deep neural networks, you try to learn features such that you can represent these patterns. Of course, when you know that this is a regular pattern that is to be continued, then you can change your feature space. For example, you can translate your signal with a Fourier transform into a signal that foresees patterns. And then you can also, with an established method, learn this. But you, as a human, have to do this translation of saying, I expect that there is a wave-like pattern, and with my expectation, I can learn this. But when you don't know that this is what you should learn, then deep neural networks are more likely to learn this feature automatically. So, of course, this remains a very hard problem to do this out of distribution learning. Yeah? And deep neural networks are not that great for out of distribution learning either. So, deep learning, you can at least try to acquire periodicity as a feature. But here you would have to manually model it. You use deep neural networks for manifold learning. What is this? Well, question first. Is this a male or a female face? What would you say? Who's for male face? Who's for a female face? I mean, this question is total garbage, right? So the question is not meaningful. And why is it not meaningful? Because all the different faces, I don't have the faces here, all these faces, they do not stand for random pixel combinations. The set of all images of male and female faces that exist are not completely random. They are limited. So, I mean, every image here is a pixel vector. And not every pixel vector makes for a reasonable face. So you can imagine that the space of all pixel vectors, this is a very large space. Yeah, let's say we only have black and white, then it would be 2 to the power of the number of pixels. Just with black and white. But not all vectors in that space are reasonable. Only a small subspace, like this one. Here you have many faces from different angles that describe a subspace of reasonable spaces. And in this subspace, we may try to learn some task like learning the orientation or male, female, or whatever you can think about. So what we then actually do is we are interested in the subspace and not in all spaces. And what neural networks try to accomplish is that they try to learn on the manifold. What is a manifold? A manifold, mathematically defined, is a subspace, or is a space that locally looks like a space of a certain dimensionality. What does this mean? Imagine you are a beetle, a small insect, and you crawl on the earth. Locally, the surface to you looks like two-dimensional. Only we know that actually the earth is a globe in three-dimensional space. But the surface of the globe looks just two-dimensional to the beetle. Actually, we are all beetles in a way, right? Because when we look around, without machinery, we cannot really recognize that easily that the space is different from two-dimensional, the space that we walk on. Yeah? So this two-dimensional appearance of the sphere is a two-dimensional manifold which happens to be placed in three-dimensional space. Here I have another picture. The data here is approximately on this blue line. And the blue line is a one-dimensional line. So you actually, when you know this manifold, you can place a data point just by providing one index. Of course, we don't care about such very low-dimensional manifolds because our data objects are not in such a small manifold. Our data objects are more like these faces. Well, I don't know what this is, like 40 pixels by 40 pixels, so 1600 pixels, and 2 to the power 1400. So there's a huge space, more than atoms in the universe. And in this huge space, we care about some small subspace, just as this is a small subspace of all the two-dimensional space. Or just as like the globe is a two-dimensional subspace. So a manifold behaves locally like this, like it appears. So a local observer cannot distinguish that the globe is a three-dimensional object. And that's basically how mathematicians define a manifold, that by local observation you don't find about it. When you then look to topology, I mean the beetle that walks in one direction all the time, at some point arrives at the same place again. And then obviously there must be something going on, otherwise that's not possible. And so with topology you look for what distinguishes different kind of subspaces. Yeah? So a ring is different subspace than a sphere. And there are things, but even a ring actually from a very small insect point of view can just be like a swim ring. Yeah, it's also just like from the point of a beetle, a two-dimensional manifold. So we also, circle is a one-dimensional manifold, but a circle exists in two-dimensional Euclidean space. A sphere is a two-dimensional manifold in R3. A torus is a two-dimensional manifold in R3. And a line in general is a one-dimensional manifold, but of course can live also in some embedding space. We use manifolds. For example, we use representations in research contributions like this, where we have an ultra-hyperbolic or pseudo-Riemannian embedding a manifold in three-dimensional space. So you have, for example, this kind of geometric object, and depending on how you walk, you are in a circular kind of subspace. Like if you walk on this ring, then there's one thing happening with your geometry. If you walk in the other direction, the performance of how you operate becomes different. In machine learning, this notion of manifold is used in a rather loose way. So it's not exactly the mathematical definition of manifold, but it comes close. And to get back to this point, we are not interested in the space that carves up this input into any male or female phase, because it doesn't matter. It's not part of the manifold that we care about. Remembering versus generalization, neural networks are really good at compression. I saw a very nice paper, I couldn't find it again later. And what did this paper do? It had a set of images, and every image had a label. And of course, what you try to do with a convolutional architecture is you try to learn what are the objects, what are the labels, what makes them. And the paper had the very simple idea, let's just confuse the labels randomly. So you randomly assign these labels to these images, and you learn again. What happened? The network learned these labels from the training data very well. Although, of course, he might be a cat, and this said dog, and here is a dog, and this said panda. There was a random assignment of these labels, and the network remembered every single training image, basically, or was very low loss. But of course, it could not generalize, because there was random input. And so the neural networks are really good at compressing the original input they had into whatever label you provide to them. And this is also, of course, a danger, because it may just learn spurious information. So that's also why regularization is so important. That's also why you need large data sizes for the neural networks. While if you take something simple like logistic regression or Bayesian neural networks, you can also work with much smaller data set sizes. Then the other thing, of course, is remembering in huge models. Of course, you all know about ChatGPT. Also, one thing about remembering, if seen often enough, I always give this example. You asked something like, who is King Charles, and in which year was King Charles born? And it gives you the perfect fact. If you ask ChatGPT, if you do the same for Stefan Staab, okay, it has seen my name. It always makes me older, yeah. So, and yeah, for whatever reason, but it's definitely wrong. And of course, well, you have to learn many parameters, and that's also very costly. This is here from our world in data, and here is some estimated flops, petaflops of what it takes to compute the up-to-date language models. So Palm was 22 or so and cost about 10 to 20 million US dollar, and now they think about ever larger models. This is a more recent version from last December, and here the cost is estimated at, this is logarithmic, so maybe that's already like $40 million for a single training run or so. So probably it's already like 1 or 2 orders of magnitudes more in the meanwhile. So when do you now want to use deep neural networks? You want to use it if the nearest neighbor is not good enough, you need warping, you have very complex features. You don't want to use it if you don't have the necessary resources maybe, unless you can use pre-trained models, because many of the language models are now pre-trained, and if you build on them, you can do pretty well sometimes with a little bit of fine-tuning. And the high dimensionality is a problem, especially for the more conventional learning mechanisms, and deep neural networks in general can learn better with a high dimensionality if you have sufficient data. But then you really need a lot of data. Yeah. Okay, so that's so much for the content. Now I also asked you to provide questions. I just had one person asking some question, and I just wanted to go through them. I mean, and if we have time, you can still bring up questions. So Hasty et al. I mean, usually I have to say I don't respond to, but this other book does it like this, because there's just too many books, yeah. But since this was the only question, I'm happy to give the answer. So Hastings et al. Describe lasso regression like this. And this is actually not really different than what we did. So what did we do? This is basically we want to minimize the loss and look for the parameters that minimize the loss. The loss consists of what is the label and what is our prediction. Our prediction is this plus this, and we compute the difference between the label and our prediction. And the prediction consists of all the different parameters times the different predictor variables. And we square this difference. And furthermore, to the loss, we add the lasso regularization, which is just lambda times the absolute values of the betas, so the size of the betas in terms of absolute values. That's actually exactly the same that we did, maybe with some differently named variables. I don't even recall this now. One side note here, this is basically a Lagrangian way of writing this lasso formulation. Namely, we want to minimize our loss. So what is the difference between what is labeled and our prediction, under the condition that the parameters should in the sum be less than a threshold. And in the support vector machine section, we looked at how do we turn such a kind of constraint into a corresponding regularization. And there was this really nice link to where this is explained graphically, how this looks for some solution with the gradients of the constraint and this function overlapping. And this is nothing else than a quadratic optimization problem. So this is the quadratic part and optimization under constraints. So that's what's happening here with linear regression with lasso. Does this clarify? There's a question, yeah? This is not defined at all. This is a hyperparameter. And this hyperparameter corresponds to this lambda, right? So if you make this lambda 0, then you don't punish at all. And 0 corresponds to having a threshold which is infinite. If you make this threshold 0, well, that would be extreme. Then your betas must be 0. Then the only beta that would be different from 0 would be beta 0. Of course, if only beta 0 is different from 0, then you have a very large loss here because you have your labels from your data and you only have a horizontal function that you look for. But of course, then what you have is only this horizontal function plays a role and all the other slopes are 0. This doesn't really matter. We liked to have this factor 1 divided by 2 because when we computed the derivative, then this 2 would be put in front and this would disappear. But it doesn't really matter because if you minimize a function or half of its function, it doesn't really matter. You end up in the same place. Of course, I mean, if you this half influences this part and not this lambda, but then you would have, if you multiply this with 2 lambda. But again, lambda is some factor, yeah, and you can switch that. Okay. Good, but I mean these are these are equivalent representations where you can go from one to the other. But you again explicitly understand what's happening here. And of course, the problem with the threshold or the problem with the lambda is with which threshold do you have good predictive performance for test cases? I mean, for your training data, it is always best if lambda equals 0. You cannot get better with your training. But for the test cases, for your test data, increasing the lambda or making the threshold smaller than infinite can improve the predictions for your test data. And the smaller here the threshold, the more of the betas will become 0. That's the effect of lasso leading to feature selection. Okay. Here the question is about that we, for a good parameter estimate in linear regression, let's say we pick whatever simple linear regression method and standardize the whole equation, which means having a mean of 0 and a standard deviation of 1. This basically means, or let's assume what happens if we don't do this. So let's assume we have here persons, and here we have income, and here we have shoe size. And we want to predict age. Stupid example, but anyway, so income as measured in, and here we have person A, B, C, D, etc. Income, okay, yearly income might be 20K, 20,000, or 50,000, or 100,000, or maybe we have someone with 10 million. Shoe size, well, quite naturally somewhere between, I don't know, what is a baby's shoe size, maybe 16? And typically less than 50 or so, yeah? I know someone with 50, shoe size 50, but it's already rather large, yeah? And maybe 43, 42, whatever, may be quite normal. So, and now you have your predictor variables, and you take for a prediction f of x is, for example, let's say 41 times beta 1 plus 80,000 times beta 2. Now let's assume that these are equally important. And now your regularization sets in. The regularization says, for example, that beta 1 plus beta 2 is less than 1,000. Now, obviously, the only way for such kind of a distribution of income to realize this is to set beta 2 to 0. So you cannot have any effect of the income because the absolute values are so extremely different. So you need to do something to put the attributes on equal footing. The attributes must be in a comparable range. And well, the easy way to do is you look at all these values and you compute the mean value, the average value, and then you just divide by this average value. Or you divide by the largest value. Yeah, there are different ways of doing things. Yeah, and you also make sure that you offset it so that the mean is around 0. So you rescale and set the mean to 0. And then the different attributes receive the same kind of importance. This may not be good enough yet because shoe sizes are more linear, whereas the income, as you see here, is more logarithmically distributed. I mean, there are incomes of 1 billion a year, right? Very rare, but happens. So it makes more sense actually to modify this further, maybe logarithmize this first, and then do this normalization towards mean of 0 with the standard deviation. And so this is all about making the attributes equally important so you can do a reasonable prediction. Okay, I hope this clarifies it. Then here we had in one of our slide decks on linear regression, we had this. And it asks here, like, how does the student t-test look like and how does ANOVA look like? I mean, the first important statement is already, we will not have an exam question where you have to compute some student t-test on your linear regression or your ANOVA. I also don't have the time now to do this in detail. I would have to prepare. Would take me some while. What, however, is the general idea? So you still get the general idea and can apply it then if you read up. What is in general the idea with a student t-test? There are variations of the student t-test. A one-sided or two-sided t-test, and then some version that appeals to this linear regression. The question is, when you have a normal distribution parametrically defined, so I'm talking about the one-sided, then the first question is, when you have a particular data point, what is the probability that this data point is from this distribution? So from this distribution here. Or what is the probability that it's not from this distribution? So obviously, when you get values that are far away here, it is very unlikely that this distribution has produced it. This is already a question that you can have for one data point. Now, what happens if you have several data points? So several data points would, for example, be all the different x's. I mean, even though one data point is here, it's unlikely, but it's possible. Now, if you have these 4 data points taken together, it more suggests that the distribution is like this or something like that. And these would be 2 different distributions. Now, it's basically the core question that's asked with the student t-test is, how probably can you reject that this comes from the same distribution? How can you reject the null hypothesis? And so basically you look at the data points and you ask, can I reject with a certain confidence, typically 5% confidence or 5 per mil confidence, that data is produced from this distribution? Be careful with this kind of significance test. It only tells you whether you can exclude it with a certain probability. This does not mean, even if you cannot exclude it, that it has to come from the same distribution. Yeah, maybe you just miss data. On the other hand, if you have sufficiently much data, you can always reject that 2 things come from the same distribution. Just because with sufficient data, a significance test or if you have a lot of data, you may have this distribution, which for all practical purpose may be exactly the same as this, but is statistically significant different. And now, in this case, we look for the question, well, is one particular attribute relevant? And for this relevance, we can also apply this kind of test. Yeah? Can I reject that this particular attribute is important, or is this unimportant? Yeah? So beta j equals 0 means the particular parameter, the particular predictor variable j, is not needed. And the alternative hypothesis is that it's different from 0, and therefore the particular predictor variable, the particular attribute j, is needed. And so what you establish with the test, you compute this test statistics, you look up in the corresponding table whether under certain degrees of freedom and certain confidence level this test statistics is produced by the t-test distribution. But it's not an exam question. It would take longer than 5 minutes to explain this in detail, and so I just try to give you the flavor of what it means. You want to reject whether data comes from a predefined distribution. And if you cannot reject it, you typically accept that it might be a good explanation. And this statistics with the student t-test builds on assumptions. It's only applicable, it's only mathematically sound if certain assumptions are given. So your data, for example, must be normally distributed. If it's not normally distributed, you cannot use this test. Actually, again, difference between theory and practice. In practice, very often, not always, the student t-test is still quite good, even if it's not produced by a normal distribution. And if you have a lot of data, the law of large numbers apply, and then it gets more and more normally distributed. So there are a number of assumptions, and then there are other tests that don't require these assumptions, and ANOVA is one of them. Especially the assumptions here are that all the different inputs are uncorrelated, which often is not the case. I mean, for example, age and shoe size, if these are two input attributes, they are somewhat related because almost only babies have a shoe size of 16 or 17. So there's a relation between age and shoe size. Okay. This is like just a flavor of an explanation, not a full explanation. But hopefully sufficient here. Yeah, and the last question, I cannot say anything about that because it asks why can we not use quadratic programming or stochastic gradient descent with Lasso? We cannot solve with Lasso analytically. We can use gradient descent with Lasso. And quadratic programming, we have a quadratic optimization problem. I don't know the details of quadratic programming now enough to be able to show you how to do this with for Lasso. I'm not sure whether some assumption is violated here. This I cannot tell you. So I'm not sure about quadratic programming, but gradient descent is effectively the method to solve linear regression with Lasso regularization. And for the quadratic programming, one always has to check conditions, and I'm not sure about these. Okay. Are there other questions? Yes. Yeah. So there is irreducible error in there. And this is you can so let's assume we have training data. Or let's assume this is our function. This is a truth that we don't know. It exists somewhere in the world, but we don't know it. What happens now when we observe? What do we do first? Because of our sensors, the true signal has some noise. And we observe this function only in a subset of all possible positions. So maybe here we observe this here we observe it here. So we have noise that just is there. Then we have a selection of data points, these x's. And if I now sample 3 x's, these are these 3 x's. If I sample another time, there are different objects that I sample, right? And then there is irreducible noise just because of the wrong sensor, but then I can try to adapt very closely to my data samples. But for these data samples and for these data samples, I can ask for how much do I adapt to them very closely. And if I adapt to them very, very closely, I have a large variance, the variance coming from the different samples I could potentially take. Potentially, because, typically I have data and that's my data. But when I sample from these two underlying functions different times, I would end up with different results. And then, of course, I have a certain bias that I decide maybe not to follow completely. And use regularization whatsoever, and that's also a mistake I do. And I typically accept that I don't have a zero bias, because if I have zero bias, I overfit to my training data. And I let other kind of mechanisms try to reduce the generalization error. But then I reduce the variation, the variance, but I increase my bias to the training data. Exactly, yeah. The irreducible error, I mean, here we have irreducible error. I mean, we do here a mistake. That's no. We only have the overall sum of these errors. So the base error was take again a one-dimensional input, and for the, let's say we have sizes of dogs and cats, or shepherd's dogs and cats, yeah? And then if here we have the height of these two dogs, now we measure dogs, shepherd's dogs, and the shepherd dog is maybe 1 meter, I don't know, an average, and some are larger, others are smaller. So we might have, for example, some are still small because they are puppies. And then we have cats. Cats are much smaller. And there's another normal distribution. Let's assume there are normal distribution. Doesn't have to be, but now when I have to decide, is this in front of me with this height a cat or a dog? I make it here with one attribute. The same thing applies for 10 or 20 attributes. Then I have to make a decision. And below the threshold, I never decide that it's a dog because the cat is just more plausible. But there are dogs that are so small. And above the threshold, there may be large cats, but I never decide it's going to be a cat. So the base error is that I make the most probable decision, but the most probable decision is still wrong because the attribute or the attributes that I have are not sufficient to delineate the two classes. Now, this is of course when you take the heights of cats and dogs, and somewhere is the threshold between the two, and they still overlap. It's sort of a simple situation. Yeah? You might say, okay, I need more attributes. But even if you have more attributes, you still run into the same problem, for probably with a smaller base error. Okay, other questions? Yeah? Sorry. You mean now for entropy or? I mean, I like to use the logarithm for basis 2, but really the behavior of the function stays the same. Of course, when we use the logarithm of basis 2, then we even have an intuitive interpretation for entropy, maybe what is one bit of information. With the basis 2, this is very intuitive. Yeah, you have a 1 or a 0, and if you have 2 bits information, yeah, you have 2 bits of information. So I like to use the basis 2 for many of these considerations, but it would also work if you use a different basis. Yeah? In sermon? In German, Um, no. I'm just considering, yeah, who corrects the exam, and team members mostly don't speak German. Yeah. No, you cannot use a calculator, but you don't need it. Oh, no, first, yeah. There was someone raising his hand, but please continue first and then. So, I mean, for example, here, this slide that I showed with student t-test statistic was mentioned. I mean, we will not create an exam question based on a slide where this was mentioned in passing, right? Of course, there may be a definition in the slides that is core and then used really, then you also need to remember it. Yeah? I mean, for example, you need to know what ridge regression and lasso regression is. You need to know the formula. This is just one example. Yeah, I don't say this is the only formula that you need to know. And yeah, but obviously there are things. If we talk half an hour about a topic, then you need to know the definition of that thing. Yeah? If I mention it and say, oh, okay, remember that also there's this thing, then you don't need to know the formula. Sometimes I said explicitly, yeah, with Adam, that this is not something where we expect you to know it, especially if you have worked with it in the exercise questions, then of course, especially, you should know it. Yeah, first the person in the background and then you. Yeah. Okay. Maybe ask for the other question first, and then I go to it. We didn't do clustering this year, so there will not be a clustering question. Okay. And for the Shapley values, let me look for it. Pardon me? Yeah. You're the next. Okay, so have to make this very, very quickly. So the question is, how much does an attribute contribute towards a particular classification, for example? And we may have a particular function, the val function, that tells us how a certain set of attributes produces a certain outcome. The problem now is we only have for a set of attributes the result. We never have for a single attribute a result, or even if you look at a single attribute, how good is it for classification? That's not meaningful because we are really interested how good is an attribute in the context of other attributes in leading to the right decision. So the Shapley value looks at, first it receives as input the value function for sets of attributes, and then asks how useful was an attribute if added to a set, and what was the difference between the two results. And now when I look at the difference of two results with or without the attribute, how do I now say that this attribute is good or relevant and not? And the Shapley values then just look at the combinatorial combination for all possible subsets with or without an attribute. Huh? Yeah, mean degrees of accuracy, or yeah, exactly. And it has some nice mathematical properties that MDA doesn't have. Okay, thanks, and much success with the exam.